Okay, picture this. Tokyo, 1943. Amidst all the wartime scarcity and chaos, you've got this physicist, Shin'ichirō Tomonaga, working away. And he's not working on just anything. He's tackling quantum electrodynamics, QED, the most precise theory we have about reality.
Yeah, incredibly accurate, but also fundamentally broken in a way.
Broken how? I mean, it's so accurate.
Well, that's the paradox, isn't it? The predictions. Unbelievably good, matched experiments perfectly. But the math underneath, it was spitting out infinities.
Infinities, like infinite mass for an electron, infinite charge, things that just can't be real.
Exactly. And worse, from a certain point of view, it didn't play nice with Einstein's relativity. It sort of assumed a single now everywhere, which relativity forbids. Causality itself was shaky.
Wow. So the stakes were pretty high. This is what we're getting into today. Tomonaga didn't just, paper over the cracks. He fundamentally rethought how quantum theory handles time.
He really did. He found a way to define what happens now, consistently, anywhere, without breaking causality. And our sources for this deep dive, they use concepts from motion theory to make his really abstract ideas feel more concrete.
Right, which is super helpful. Our mission here is to follow that path, see how Tomonaga sliced time, how he dealt with those crazy infinities, and why these fixes from way back then are still so vital today.
Yeah, for everything from fundamental physics to quantum computing.
Okay, so before we jump right into the physics fight, let's get that vocabulary map sorted. Using these motion theory ideas really helps ground things. When we talk about time in this framework...
Right. Forget the universal clock ticking away. In this view, time is just. It's a measurement of movement, or you could say the rate of change within a system. It's local rhythm.
Okay. Local rhythm, I like that. And fields, like electromagnetic fields, not some invisible goo, right?
Oh, no, not goo. Think of them as patterns in motion. Gradients.
Yeah.
Tendencies for how things move or synchronize. Motion gradients.
Got it. And mass. That's not just how much stuff something has.
Not quite. It's more like resistance to retuning. How hard is it to change a pattern's rhythm? How much does it resist syncing up differently? That's mass.
Resistance to retuning.
Interesting.
And just quickly, gravity.
Ah, yes. Gravity in this picture is simply this tendency for structured motion to move towards denser synchronization, seeking coherence.
Okay. Motion gradients, resistance to retuning, seeking coherence. That helps. Let's use that. All right, so QED back in the 30s, it had these cancers, you could call them. We mentioned the infinities, which we'll get to. But that time problem, that seems even more fundamental. Why exactly did the old QED clash with relativity?
Well, the standard way of doing things, the Schrödinger equation framework, it assumes you can describe the state of the entire universe at one single moment in time, a global now.
Like a snapshot of everything, everywhere, instantly.
Exactly. But Einstein's special relativity tells us that's impossible. There is no universal now. My now and your now are different if we're moving relative to each other, especially over large distances. Simultaneity is relative.
So the very foundation of how QED calculated change over time was non-relativistic. It didn't respect the basic rules of space-time.
Pretty much, yeah. Which opens the door to violating causality, effects happening before there are causes, information seemingly traveling faster than light. It was a huge theoretical breakdown.
Okay, that's bad. So how did Tomonaga fix it? What was his big leap?
His insight was realizing you don't need that flat global time slice. He showed that the quantum state could be defined not on a fixed time, but as a functional of, wait for it, an arbitrary space-like hypersurface.
Whoa, okay, functional. Arbitrary space-like hypersurface. Let's break that down. Space-like hypersurface.
Right. Think of space-time like a block.
Yeah.
A normal time slice is like a flat cut through it, representing now everywhere.
Yeah.
A space-like hypersurface is more like a flexible surface you can push through that block.
Flexible how?
It can be curved, bumpy, basically any smooth slice you like. With one crucial rule. At no point can the surface itself be moving faster than light relative to any other point on it. It always have to respect the local light cone structure.
So it can bend and warp, but it can't become vertical, so to speak. It can't allow for instantaneous connections across space.
Exactly. It maintains causality locally everywhere on the slice. He called it a causal scalpel. And the amazing part, his equation, the Tomonaga-Schwinger equation, showed that the physics, the actual outcome of how the state evolves.
Doesn't depend on the shape of the slice you chose.
Precisely. As long as it's a valid space-like slice, You can sweep it through space-time however you like, and the physics comes out the same.
Okay, that's incredibly elegant, but why? What guarantees that consistency?
Microcausality. That's the key. It's the condition that physical operations or measurements at 2 points, separated by a space-like interval meaning light, can't cross between them and that time must commute.
Commute meaning the order doesn't matter. Doing A then B gives the same result as doing B then A.
Yes. If they can't influence each other instantly because they're too far apart relative to the time difference, then the order you consider them in can't change the physics. Tomonaga built this principle right into the foundation.
So the physics becomes truly local. It respects Einstein from the ground up.
Absolutely. And thinking in terms of motion theory, our sources put it nicely, physics is just local phase adjustment. You can slide your phase cut, your definition of now, through the system any way you want.
As long as you respect the speed limit, see?
And the way things interact, the couplings, they ensure you get the same consistent local story. He basically gave us a working relativistic definition of local synchronization.
Okay, that sorts out the time problem, which is huge. But now, those infinities. This is where things often get described as mathematically suspect, even today sometimes, renormalization.
Yeah, this was happening around the same time, with Tomonaga, Schwinger, Feynman, Dyson, all contributing pieces. And the problem was just stark. You try to calculate, say, the energy an electron possesses just by interacting with its own electromagnetic field.
It's self-energy.
Right. And the answer the theory spat out was infinity.
Not just a big number, literally infinite.
Infinite. Same for corrections to its charge. If you tried to calculate things using perturbation theory, adding up small corrections, you got an infinite series of more infinities. It looked like the theory was fundamentally nonsensical.
So the joke about physicists just sweeping the infinities under the rug, was there some truth to that feeling back then?
Oh, absolutely. To outsiders and even many physicists, it looked like they were just defining infinity finite number and calling it a day.
Yeah.
Felt like a cheat.
But it wasn't. What was the real insight?
The insight was subtle but profound. It wasn't about making the infinities disappear. It was about realizing they corresponded to quantities we could never actually measure. They were part of the baseline, not the shift.
Explain that. Baseline versus shift.
Okay, think about an electron. The bare electron, completely isolated, without interacting with anything, not even its own field. That's a theoretical fiction. We can never see that.
Right. It's always interacting, always dressed by its quantum field fluctuations.
Exactly. So the infinite self-energy, the infinite bare charge, those are properties of this fictional bare particle. What we can measure in the lab are the properties of the physical dressed electron, its actual mass, its actual charge.
So you measure the real thing, like its response in a magnetic field, its spectral lines.
Yes. You take those measurable spectra, those observable outcomes, and you use them to define what you mean by 1 unit of charge or 1 unit of mass for the electron.
Ah, so you anchor your definitions to reality.
Precisely. You perform the calculation with the bare quantities, which gives you infinities all over the place. But then you say, okay, this whole infinite chunk corresponds to the difference between the fictional bare electron and the real one I measure. I'll absorb that infinite difference into my definition of the physical mass and charge.
Those absorptions, are those the counterterms?
That's them. They are precisely the infinite terms you need to subtract from the raw calculation to make your predictions for observable phenomena like the Lamb shift or the anomalous magnetic moment come out finite and match experiments.
Okay, let's use our motion theory map again. The vacuum is a catalog of permitted fluctuations, right? Background phase noise. How does renormalization look like coherence bookkeeping?
Well, you've got two kinds of motion, or phase effects. There's the baseline, this sort of universal, unseeable background hum, the phase offset that everything has just by existing. It's infinite, maybe, but irrelevant because it's the same everywhere. Don't worry about it.
Like trying to measure absolute altitude instead of height difference.
Good analogy. Then there's the shift, the specific observable change in rhythm or retuning that happens because of interactions. The Lamb shift is a perfect example, a tiny energy shift in hydrogen caused by vacuum fluctuations. That's what we can measure.
So the counterterms are the ledger entries needed to cancel out the unobservable baseline noise.
So that your calculation only reflects the measurable finite shift. It ensures your theoretical books balance against the books of experimental reality.
Okay, it's not hiding infinities, it's isolating the change. And the results are, well, Famously accurate, QED predictions match experiments to parts per billion or even trillion.
Astonishingly accurate. It's arguably the most successful scientific theory ever, quantitatively.
Yeah.
And that quote from the source material really nails it. The vacuum edits your spectrum, measure the edit, pay the coherence bill.
Pay the coherence bill. I like that. It forces you to focus only on what actually changes, what you can actually see. Now, Tomonaga wasn't just focused on fixing QED's immediate problems. He was also thinking deeply about foundational principles like gauge symmetry. How does that connect back to his whole time-slicing idea?
It's deeply connected. Gauge symmetry, or what our sources call phase freeding, is absolutely central to QED. In essence, it says that the fundamental physical reality doesn't change, even if you change the mathematical labels you use for the quantum fields. Specifically, you can shift the phase of the electron field and the electromagnetic potential together in a certain way.
And the observable physics forces, energy stays exactly the same.
Exactly the same. It's like changing the key of a song, but keeping all the relative notes the same. The melody, the harmony, they're unchanged. The physics only cares about differences in phase, not the absolute value.
Okay, so why was it so important for Tomonaga that this symmetry held true locally on every point of his arbitrary space-like slice?
Because if the physics did depend on the specific mathematical label, the specific phase choice, then calculating the state on different slices or even different points on the same slice using different descriptions would give you different inconsistent answers.
The whole independence of the slice thing would break down.
Completely. Gauge invariance is the mathematical guarantee that the description is redundant in just the right way so that the physical predictions are robust and only depend on physically meaningful quantities. It ensures that your arbitrary slice method is consistent. It forces locality and causality into the structure of the interactions.
So it's not just an elegant mathematical feature, it's actually what makes the relativistic description work. It ensures the physics cares about the relationships, the voltage, phase difference, and the current, how phase changes flow, not the arbitrary labels.
Precisely. Tomonaga rigorously applied this. If your state evolution calculation violated gauge invariance on that arbitrary slice, you knew you'd made a mistake somewhere. It's a fundamental consistency check.
And he took these ideas beyond QED too, right? Into nuclear physics. That seems like a much messier domain.
Oh, much messier. He worked on meson theories, trying to understand the strong nuclear force, and also on general many-body problems in quantum mechanics. The motion theory perspective offers a neat way to think about this.
How does it frame something complex, like an atomic nucleus?
Instead of thinking of it as just protons and neutrons bumping around, you picture it as a hierarchy of coupled motion loops. You have the nucleons themselves, which are complex resonant structures, and they're constantly interacting via the exchange of other particles, like mesons.
So the mesons aren't just particles being thrown back and forth.
It's more like they represent the patterns of the coupling itself. The force is the structured coupling. The exchange is really about phase handoffs between these different loops of motion, the nucleons, and their surrounding meson halos.
And the properties of the nucleus, its stability, its energy levels, emerge from this complex dance of coupled rhythms.
Exactly. And just like in QED, the presence of that surrounding cloud, that environment of virtual mesons, it subtly shifts the energy levels, the measured spectrum of the nucleons. It's all about calculating those observable shifts arising from these local causal phase adjustments and couplings.
Okay, so Tomonaga laid this incredibly robust foundation 80 years ago. What does it actually buy us today? For someone interested in, say, quantum tech or cutting-edge experiments, it feels very theoretical.
It might feel theoretical, but it underpins almost everything in modern particle physics and quantum field theory. It gives us two essential tools we rely on constantly. First, locality without mythology. We have a framework where we know change happens locally, through causal connections, respecting relativity, without needing some universal clock.
No spooky action at a distance needed, just local phase transfer.
Right. And second, no infinity worship. Renormalization taught us to define our physical quantities based on measurement and focus only on observable changes, the retunings. We don't get paralyzed by unobservable bare quantities.
That focus on observables seems key, and the sources mention specific concrete experiments happening now that are essentially testing Tomonaga's ideas in hardware. Let's talk about those. First one, vacuum editing with entropy accounting. What's that?
This really gets at the pay the coherence bill idea from renormalization. You know how the vacuum isn't empty but full of potential fluctuations?
While in the phase noise catalog.
Well, labs can now engineer that vacuum. They can squeeze it, altering the kinds of fluctuations allowed in a specific region, often using carefully tuned electromagnetic fields or cavities. Then they put an atom or another quantum system inside this engineered vacuum.
And they can see the atom's properties change, like its energy levels shifting or how long it takes to decay.
Exactly. You can measure those shifts, the edit the engineered vacuum makes to the atom spectrum. But here's the crucial addition inspired by this line of thinking. You also need to measure the energy cost, the calorimetric power, required to maintain that special ordered vacuum state.
Because creating that non-standard vacuum order takes effort.
It has to. The prediction, framed as the coherence-cost equality, is that the amount of extra coherence or order you create in those vacuum modes must be precisely balanced by an entropy cost somewhere else, usually heat dissipated in the equipment maintaining the state. You fundamentally have to pay for coherence. It's like thermodynamic bookkeeping for the quantum vacuum.
Fascinating. You can't get that order for free. Okay, what about testing microcausality directly? That sounds like testing Tomonaga's time slicing.
It is. You could do this using quantum simulators. These are controllable quantum systems, like strings of trapped ions or arrays of neutral atoms held by lasers. You can precisely control how they interact.
You can program their interaction.
Yeah, and crucially, you can control the effective speed limit for information traveling between them, their light cone. So you can set up an experiment where you perform a sequence of operations, quantum gates, on different parts of the system.
Okay.
And you can try two different sequences corresponding to sweeping two different space-like slices through the simulation. If the operations in those sequences are truly space-like separated, according to the programmed light cone, meaning one couldn't influence the other in the time allowed,
then the final state of the quantum simulator must be identical for both sequences.
Must be. That's a direct test of Tomonaga's principle. But if you deliberately program the interactions to act faster than the light cone allows, making them effectively superluminal within the simulation,
then the results from the two different orders won't match.
Exactly. The equivalence breaks down. You'd see experimentally that the order matters, proving that the causal structure Tomonaga assumed is physically real and necessary. It's literally testing microcausality on a chip.
Wow. And the last one mentioned is spacelike slice tomography, using ultrafast lasers.
Right. This pushes it to incredibly fast timescales attoseconds, which are billionths of a billionth of a second. The idea is to probe different parts of, say, a molecule or a nanostructure simultaneously or almost simultaneously with multiple laser pulses.
Okay.
You then reconstruct the system's dynamics based on the timing and results of these probe pulses. The question is, if you analyze the data, assuming different time orderings or different slices for these pulses, do you get the same picture of the dynamics?
And Tomonaga's theory predicts.
It predicts you'll only get a consistent matching reconstruction if the probe pulses were genuinely space-like separated, if no signal could travel fast enough between the points being probed in the time between the pulses. If you try to reconstruct, assuming an order that violates the light cone, the physics should look inconsistent. It's another way to verify that reality respects local causality, even down to the attosecond scale. Hashtag outro.
So Shinichiro Tomonaga, working in pretty isolating conditions back in the 40s, really did give physics this causal scalpel. He showed how to cut through space-time without breaking relativity.
He formalized local synchronization, made sense of fields as these actionable motion gradients, and fundamentally taught us that physics is about observable changes and that, well, coherence isn't free. You have to balance the books.
That ability to slice time how you like locally and trust that the global picture holds together, that's his huge legacy. I think the best takeaways, the things to really remember, are those one-liners from our sources.
Yeah, they capture it well. First, don't search for a universal now, slice locally and agree globally. It's about perspective and consistency.
Right. And the second about renormalization. Renormalization isn't sweeping dirt, it's balancing the phase books. It's about honest accounting of what we can actually measure.
Exactly. He gave us a way to calculate within quantum field theory that respects causality and focuses on reality.
So here's a final thought to leave you with. Tomonaga showed reality evolves without lying to causality. But that coherence-cost equality, we talked about the idea that creating order in the quantum vacuum must have an entropy cost.
That you have to pay for coherence.
Yeah. What does that really mean for the future? If we dream about technologies that may manipulate the vacuum for, say, free energy or build perfectly stable quantum computers, does this principle impose a fundamental thermodynamic limit? Is there always a cost, a bill to be paid somewhere else in the system for any order we try to impose on the quantum world?
That's a really deep question, isn't it? What are the ultimate thermodynamic limits on engineering reality itself? Something definitely worth thinking about.